Okay, so in this video, I want to go over quite a nice graph theory problem. So the theorem that we want to solve is, I'll put it in a little box. So for any simple graph G, the number of edges of G, which I notate with E of G, is less or equal than n over n choose 2, sorry, where n is the number of vertices of G. So we're going to start with our base case. If we imagine n equals 0, then that's a that doesn't really make any sense. That's a graph with no vertices. So clearly that's going to be the case that it's going to have 0 edges. So because n choose 2, well then that means n choose 2 is going to be 0 too. There's no vertices. If you've got 0 objects, there's how many ways can I choose 2 from that? 0. So that's going to work. And for n equals 1, then if we have one vertex, like I've got here, that is a trivial that's a trivial graph. There's no edges. You might ask, well, we could have that, but that's a loop. Then that breaks simplicity. So obviously it's going to have 0 edges. So we're going to get 0 less or equal, well, what's 1 choose 2? What's 1 choose 2? If you put it into your calculator, you will get 0. Because if I have one object, so if I've got one box, how many groups of 2 can I make from that? Well, none. So that means there's, how many groups of 2 can I choose from that? None. So that means we have 0 less or equals 0, which works. So the base case is true. So basically, our strategy is going to be induction. I always write it in the form of strong induction, but weak induction will work just as well. So basically, I'm assuming that for k equals 0, 1, 2, all the way up to some arbitrary positive integer n, that the statement of the theorem holds. So that is, for any simple graph with 0, 0, 1, 2, 3, 4, all the way up to n vertices, then the number of edges is going to be at most or less or equal than the n choose 2, where n is the number of vertices. So I'm assuming that, and you may notice, well, why have you assumed it all the way up to, why have you assumed it for all of these? Why haven't you just assumed it for n, and then you're trying to prove it for n plus 1? Well, this is called strong induction. And to be honest, I just prefer to write it like that because it's a little bit more useful. There's not a lot of theorems that benefit from strong induction over weak, but the two are equivalent, okay? So basically, that means for the nth case, this will hold. So we're assuming it will hold, and we want to prove that if it holds for the nth case, that it proves for the n plus 1th case, if you want. So the trick to this is what I've written in blue. I'm just going to rub it out. I'm just going to explain how I've arrived at that statement in blue. So the idea is, if we have a graph with n vertices, what will happen if I add another vertex? Because that will essentially get me from the nth case to the n plus 1th case, and I can examine the two. So if I have a graph with, say, let's think about an example. Let's imagine a simple graph. These are simple graphs, right? They haven't got any loops. They haven't got multiple edges between two vertices. So I got, a nice simple graph. Really badly drawn though, but a nice simple graph with 3 vertices, 3 edges, right? I'm going to add another graph. I'm going to add another graph. I'm going to add another vertex in red there. Only put it in red just so we know I've added it. Now, if we look at the form of this inequality, it is the number of edges is at most or less than or equal to something. So a good question to ask is, if I add one more vertex, what is the maximum number of edges that I can add? Because that will result in inequality of this form. So, if I have this red vertex added, then that means I can add at most 3 more vertices. Not 3 more vertices, sorry, 3 more edges. And let's see if that's true. What if I add another edge somewhere? Say there. Well, I've just broken simplicity if I do that, because now there's 2 edges between the vertex here and the vertex here, so that doesn't work. And it's going to be the same with any other vertex on this graph. So that means if I add one more vertex, so add one vertex, that means we add at most, and it's only at most because we might not have, say, this edge here. It's the maximum case. I add at most 3 edges. Well, what if I have a graph with 4? What if I have a simple graph with 4? What if I have a simple graph with 4 vertices? So it could look something like could look like that, I guess. So it looks a bit different, but it's a simple graph because there's no loops and there's no multiple routes. So if I'm at one vertex, there's only one edge that gets me to another vertex, and so on. If I add another vertex, then I can add 1, 2, 3, 4 edges, and clearly I can't add any more. I can't add any more edges because then I would violate the multiple edges condition. So I think we can quite nicely extend that. I mean, I think you could basically prove that by induction. You could say, if I add one more vertex to any graph, then I add n more edges. Okay, so we're going to write that. That's sort of like a lemma that helps us prove this theorem. So I'm not going to prove that rigorously because I think it's quite obvious, but you could probably prove that by induction. So our lemma is if we add one more vertex to a simple graph, at most n edges are added if we are to maintain simplicity. What have I done there? Okay, so that lemma is really helpful for us, and as I said, you could prove it by induction really easily, and it obviously holds for the simple cases like 1, 2, 3. If it holds for the first n cases, then if you add another vertex, then you can see that obviously you can only connect that one vertex to the n vertices that remain, because if you add it, if you connect it n+1 times, then it's going to be an extra edge. So it's easy to prove that, so that's fine. So I don't want to get too sidetracked. So now let's actually go back to our induction. So let's say so we're going back. So we've assumed that the theorem is true for everything up to n. So zero vertices, one vertex, two vertices, all up to n vertices, where n is an arbitrary positive integer. So we say that G dash is a simple graph, so it's simple and has n+1 vertices. Now, what I can say is that the number of edges of G dash is, well, I don't know what it is exactly, but I know that it is going to be less or equal than the number of edges of G, which we assume has n vertices, plus, so this in blue, plus n. We did that, that's just using the lemma, so we have G dash has got n+1 vertices. Then if you have, or I'll tell you what, if you are at, if you have a graph with n vertices, then to get to the simple graph with n+1, you would add one vertex, and then you'd have at most n more edges. So we know that this is true from the lemma. So what we can write now is by induction, we can apply the induction condition to E of G, because that has n vertices, and we assume that the theorem would work up to n vertices. So by induction, I can replace E of G with, or I can say that E of G dash is less or equal than E of G plus n, but E of G is less than or equal to n choose 2 by the induction hypothesis. So I can say that E of G dash is less or equal than n choose 2 plus n. There we go. So we're actually really close to the answer now, and I can, I'm trying to think of the easiest way to explain why. So, and choose 2. Yeah, and basically what we can do now is say, well, if I have, what I want to show basically is that, so I'm going to say RTP, and I'll put it in green. So RTP, I want to show, so RTP means required to prove that E of G dash is less or equal than n plus 1 choose 2. But what does n plus 1 choose 2 look like if I simplify it down? Well, n plus 1 choose 2 is actually a really interesting little result, because if I work it out, it's going to be n plus 1 factorial over 2 factorial times n plus 1 minus 2 factorial, which is just n minus 1 factorial. You know, n plus 1 take away 2 is minus 1, so I get that. I get that. But n plus 1 factorial is just n plus 1 times, I can just leave it like that, n plus 1 times n minus 1 factorial. So I can then put that over 2 factorial times n minus 1 factorial. And we should notice that the n minus 1 factorials cancel out. So I end up with n times n plus 1 over 2 factorial. But 2 factorial is just 2 times 1, which is 2. So we end up with half n times n plus 1. So what we're really trying to show is that the number of edges on G dash is less or equal than 1 plus 2 plus 3 plus 4, because we know this is the sum of the first n natural numbers, which is quite a cool result, really. So really, that is what we're trying to prove. So I haven't proved that what I have in green is true, but I know that the expression that I want to get to is equivalent to this. So if I can show that this expression is equivalent to half n plus 1, I will be done. I will have proven my theorem. So let's go back to E of G dash. So E of G dash is, we know by the induction hypothesis, less than or equal to n choose 2 plus n. And let's simplify this down. So n choose 2 is n factorial over 2 factorial times n minus 2. Oops, sorry, my pen is going a bit dodgy. Factorial. And I have my plus n on the end. Now, similar to what we just did, I can simplify all this business down. I can say, so E of G dash is less or equal to n factorial, which is n times n minus 1. And then, it would be n minus 2, then n minus 3, and n minus 4, all the way down to 1. But I could just write that as n minus 2 factorial. So n factorial is just n times n minus 1 times n minus 2 factorial. That's a really useful trick. And obviously then on the bottom, I haven't changed it. I've got 2 factorial n minus 2 factorial. And then I'm adding n on the end. And let's have a look what cancels. Well, the n minus 2's cancel. So that just leaves me with n times n minus 1 over 2 factorial. 2 factorial is just 2. So I really have half n times n minus 1 plus n. Now you might notice what this is already. This is the sum of the first n minus 1 natural numbers, and that's n. So if we add them up, we're going to get the sum of the first n natural numbers. But let's prove it algebraically just so we can satisfy our inner algebraist. So if we take out a factor of, I don't know, let's take out a factor of half n, then I get n minus 1 plus 2n. Now 2n, I made a mistake here. No, that should just be 2. I have made a mistake, because obviously half n times 2 is just n. Sorry about that. 2 minus 1 is 1, so we have half n times n plus 1. So that means that E of G dash is less than or equal to half n times n plus 1, which we proved earlier is equivalent to saying that because obviously half n plus 1 is the same as n plus 1 choose 2, it's equivalent to saying that we have E of G dash is less or equal to n plus 1 choose 2. So basically what we have shown is if we assume that the induction hypothesis holds for k equals 0, 1, 2, up to n, then so we're saying, I don't know, so if I let P be that the induction hypothesis is true, then basically if P is that the induction hypothesis is true, we've shown that P for 0, 1, 2, blah, 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 is true. So that holds up to n. We have shown that if this holds, then P of n plus 1 holds. Therefore, by induction, the proposition P holds for all n. That's a really dodgy for all symbol, but for all n in the natural numbers, and 0 as well. So basically that proves it for every case. So we know now, therefore, for every simple graph, the number of edges, so for every simple graph G, the number of edges of G is less or equal than the number of vertices n choose 2, which is what we were to prove. So I can say therefore all n in n, and I can say QED, or I can use my little box, and that's it.